Okay, so I think we'll get started. So we're very happy to have Peihan visiting us this week. So Peihan recently finished her PhD at Berkeley and is about to go become a researcher at Visa Research. And in between, she's been gracious enough to come visit us for the week. And today she's going to talk about some work, I think, from an internship, prior intern. So I should also say Peihan was our intern 2 years ago, but this time she's going to talk about work from a more recent internship at Visa. About threshold cryptography.
Thanks, Melissa, for the introduction. Before lunchtime, I'm going to present some PASTA, which is short for password-based threshold authentication. It was joint work with Shashank Gravel, Pavan Mahaso, and Pratim Mukherjee at Visa Research. It was published in CCS last year. Okay. So the first question you want to ask, what is PASTA trying to solve? Let's start with the example. When you try to log into Dropbox, there's an option of signing in with Google. And how does that work? The standard mechanism of doing this is called OAuth, and it works as follows. There are three parties in this protocol: a Google server, which holds a secret key, a Dropbox server, and your computer. And when you try to log into Dropbox, you're using your username and password of your Google account to somehow request for a token. And then the Google server will verify if the password is correct or not. If it's correct, it will use a secret key to generate a token. It could be a digital signature in this case. And then the user can just forward this token to Dropbox. And then Dropbox will verify if this is a correct token generated by Google and so on. If everything looks good, it will give you access. Okay. In this protocol, if the server is somehow attacked or corrupted, then there will be two issues. First, the secret key will be leaked, so the adversary can generate any token to get access to any Dropbox account. And the second issue is that the user's password could also be somehow leaked. I will elaborate more on that later, but let's look at a second example called JSON Web Token. This is my Gmail app on my cell phone. Whenever I want to see my emails, I just open the app and it's automatically logged in. I don't have to type in my password every time. I just type in once at the very beginning. So how does that work? It's very similar as before. There are three parties: a Google server holding a secret key, a Gmail server, and my cell phone. When I type in my password, I am actually using my username and password of my Google account to somehow request for a token. And then the Google server will verify if the password is correct or not. If it's correct, it will use the secret key to generate a token. It could be a digital signature or a MAC. And then I can just store this token locally on my cell phone. Later, whenever I want to access Gmail, I just send this token to Gmail. And then Gmail will verify this is a valid token generated by Google for me. Everything looks good. It will give me access. And now if the server is somehow corrupted, again, there are two issues. First, the secret key is leaked, so the adversary can generate any token to access any Gmail account. And second, the password could also be somehow leaked. And the last example, every day when you come to office, you log into your account, and then you get access to internal resources like internal websites, printers, and so on. And a widely used system is called Kerberos. And it's also very similar as before. There are three parties, a server holding a secret key, user's computer, and internal web resources like a printer. And then when you log into your computer, you're using your username and password to request for a token. The server will verify the password is correct and then generate a token. It could be a MAC in this case. And then you store this token for the day locally, and later whenever you want to print something, you forward this token to the printer, and then the printer will verify everything's correct and then print the things for you. And again, if the server is corrupted, there are two issues. First, the secret key is leaked, so you can generate any token to get access to any internal resources. And second, the user's password could also be somehow leaked. And now I will explain how this password is leaked. But before that, any questions? Yeah.
So in the OAuth thing, so the token goes back to the client, or does it go directly to the other service provider?
It goes to the client, and then the client is actually storing the token locally. And later, whenever you want to access Gmail, you have to send this token to Gmail.
So that's the second scenario you said, like the JSON Web Token.
Oh, yeah.
I was talking about the first one that you said, OAuth.
Oh.
So the web token is going back to the client, or is it going directly to the
I'm not familiar with the exact mechanism, how it works. It could be either way, I think.
And for the Gmail example, what is the lifetime of the token? Because it is.
It depends. Yeah, it depends. It has to be short. You have to refresh the token every once in a while. Okay. Yeah, that's a good question. Yes.
Since you say in Kerberos you're using a Mac, and then the printer sees the thing signed with the Mac, does it send it back to the server, and there is some other communication, or does the printer also have the Mac signed?
Yeah, that's a very good question. Actually, in this case, the printer also has the secret key. So if the printer is somehow corrupted, then the secret key is also leaked. But the thing is, if the secret key is leaked, we see it as one issue, but the other issue, a separate issue, is the user's passwords. So in that case, if the secret key is leaked, then you can replace it with a new secret key. And then, after that, you can use this new secret key. But if the user's password is leaked, it's like forever. You have to change your password in other websites as well. Yeah. Okay. Any other questions? Okay. Now let me explain how this password is leaked. So in a password-based authentication scheme, usually how it works is the following. When the user signs up, it will send its username and password, hash of... Password? 1 second. There is some order. So in a password-based authentication system, there are two parties: a server holding a secret key and a user using its username and password to request for a token. And then the server verifies the password is correct or not, and then generates the token. And now, if the server is corrupted, then there are two issues. First, the secret key is leaked, and then the password is also somehow leaked. So the password safety happens in a lot of password-based authentication scheme, and the issue arises as follows. When the user signs up, it will send its username and hash of its password to the server, and the server will store them locally. And later, when the user is requesting for a token, it will send its username and hash of its password to the server. So the server can verify if these two hash values are the same. If they are the same, then the password is correct. So it will issue the token. So if you think about it, when the server is corrupted, then the password is not immediately leaked. Only the hash is leaked. But what the adversary can do is that he can try different possible passwords and see if any of these hash values match this hash value that's stored locally. This is what we call offline dictionary attack. So this, if you're familiar with sorting mechanism, adding a sorting is not solving the problem fundamentally. The adversary can still try hash on the possible passwords and the sorting. So this issue is still there. And because in reality, users' passwords are usually chosen from a relatively small space, such kind of attack could succeed with very high probability. And this actually happens a lot in reality because of data breaches in a lot of companies like Yahoo, eBay, Uber, and a lot of other companies.
Can I ask you a question?
Yes.
You said offline, you meant that some other party is able to query the server, or it's just the server itself being malicious?
Yeah, it's just the server itself being malicious, and everything is running locally. You don't have to talk to any online server. That's why we call it offline attack. Yeah. But that's a good question. We will talk about online attack later in this talk. Okay, and then even if you think it more generally, this issue seems unavoidable if there is a single server. For example, even if you change the request protocol, pick your favorite request protocol, at the end of the protocol, if the user is using a correct password, it will generate a valid token. Pick your favorite protocol, this issue is still there. Let's see why. So in this new protocol, there's no hash stored in the server, on the server side. But in this case, if the server is corrupted, what he can do is that he can run this protocol in his head and pretend himself to be an honest user and try different possible passwords and run this protocol and see at the end of the protocol whether he will get a valid token or not. Because everything is running on his head, this is still an offline attack. You don't have to talk to any online server. So this issue kind of is still there if there is a single server. It's kind of inherent. Any questions so far? Okay. And here comes our goal. Because of this inherent issue, because of there is a single server, our goal is instead having a bunch of servers and having the secret key somehow shared among the servers, such that even if a subset of the servers are corrupted and colluding, we still have the following two guarantees. First, the secret key is secure, and second, the user's password is secure against offline attack. Okay, is this goal clear? Okay, and here is our contribution. We formalize our goal of password-based threshold authentication. We motivate the problem and formalize a game-based security definition. And then we present a PASTA, which is a framework of construction that works for various types of tokens. We have minimal round complexity and very low computational and communication complexity. And finally, we present some implementations and experimental results. And next, I'm going to give you the definition of PBTA. I will not go into the details of the definition, but just to give you a high-level idea how it is defined, how it works. And then I will tell you how PASTA works. Okay. So in the PBTA scheme, first there is a global setup phase where we have a bunch of servers and a secret key shared among them. That's the end of global setup. And we have the guarantee that any T servers can jointly recover the secret key. But on the other hand, if up to T-1 servers are corrupted and colluding, they cannot recover the secret key. It is very standard threshold cryptography. And then for every user, they have to sign up using its username and password. It has to sign up at every server. And then after the sign-up phase, it again can use the username and password to request for a token. And in this case, every server will use its partial secret key to generate a partial token. And then if you have T-valid partial tokens, you can jointly recover a valid token. On the other hand, if up to T-1 servers are corrupted and colluding, they cannot recover the user's password by offline attack or forge a token or recover the secret key. Yes?
When the user signs up with each server, are they signing up with the same password across all the servers?
Yes.
Or different?
Yeah, the user only remembers one password. Yeah. Any other questions?
So why can't then any server recover it? It depends on how the registration phase works, right?
Yes.
So if it's still storing a hash of the password, which it could, it can mount offline attack.
Yeah, we designed a protocol which includes all the global setup, the users sign up, and requesting for a token. It's not using arbitrary protocol. Yes.
So the servers are not allowed to talk to each other?
Yeah, they don't talk at all.
Is that inherent or just for efficiency? Or?
Yeah, it's just for efficiency. We just want to minimize the interaction between the parties. Yes.
Does each server here belong to a different identity provider?
Identity provider?
Yeah. One server runs by Facebook, one server run by Google.
It could potentially be in that case, but we're just providing a protocol that has these guarantees. We don't restrict whether they have to they have to belong to one company or different companies. We just have the guarantee that if after T-1 servers are corrupted, they cannot recover the secret key or guess the password. If T servers are correct, then you can recover a token. Does that answer your question?
There would be some delay in the user experience,
Yeah, that's true.
right?
And it's up to the. Actually, later in this talk, you will see the performance. And actually, the main delay of this protocol is the communication between the servers and the client. The computational overhead is very low.
But it would be bound by the slowest server among the T server, right?
Yeah, that's true.
Okay.
Yeah, that's true.
But also the question that Dana asked is if they're all, let's say, servers run by the same company, for example, do you need an assumption of no communication between the servers? Like, because then if one of them's corrupt, you don't know if they infect the others. So you're assuming, do you need to assume that the servers do not communicate with each other?
Actually, in our definition, our protocol is defined such that there is no interaction between the servers, and that's because we want to minimize the communication and get the best efficiency. But in terms of communication between the servers, I guess if there is, for example, if there is only one server corrupted, and even if you assume communication between the servers, if the other servers are not, if you assume the other servers are not corrupted, then that's fine because they're not colluding. They're not allowed to collude. But if you're allowing them to collude, then it's assuming more servers are corrupted. Yeah, does that answer your question? Okay, any other questions? Okay, cool. So that's the problem that Pasta is trying to solve. And next I will tell you how Pasta works. And to make our pasta, we need two ingredients. One ingredient is called non-interactive threshold token generation, or NITTG for short. We know in the literature NITTG schemes for various types of tokens. And then the other ingredient that we need is called threshold oblivious pseudorandom function, or TOPRF. It was introduced by Jiraki et al. In 2017. And we formalize a game-based definition for our needs, and we prove their protocol is also secure under our definition. And then we combine these two ingredients to make our pasta. So next, I will tell you what is NITTG and what is TOPRF and how to combine them. So first, NITTG scheme is a token generation scheme where there are a bunch of parties and the secret key for the token is shared among them. To generate a valid token, every party has to use the secret key, the partial secret key, to generate a partial token. And then we have the guarantee that any T partial tokens can be used to recover a real token. And on the other hand, if up to T-1 token key shares or partial secret keys are corrupted, they cannot be used to forge a token or recover the secret key. So this is a scheme for NITTG. Yes?
What? Do they must have some coordination on which token they're producing or something like that? Do they all have to have the same random nodes or the same input or something?
Oh, they have the same input, yeah. They when they are trying to generate a token, they're generating the token for the same message. Yeah. Okay, yeah. So given this primitive, we can already come up with a naive solution. And the naive solution works as follows. First, there is a global setup where the secret key is shared among the servers just using NITTG. And then when the user signs up, it again sends its username and hash of its password to every server. Every server stores it locally. And then when the user is requesting for a token, it sends its username and hash of its password to every server. And then every server verifies the correctness of the password. If it's correct, it will use the partial secret key to generate a partial token. And then if you have T-valid partial tokens, you can combine them to get a valid token. In this case, the secret key is secure in the sense that if up to T-1 servers are corrupted, they cannot recover the secret key. That's a security guarantee by the NITTG. But the password, the user's password is not secure against offline attack. Even if there is a single server corrupted, he can already try different possible passwords and see if there is a match. So this is not secure enough. Yes?
So if I have everyone corrupted server, can I just send the hash to other servers to reconstruct the whole token?
Yeah. That's what we call an online attack. You have to talk to other servers. In this case, this is offline, meaning that it is just running on itself.
Okay.
You don't have to talk to any other. Yeah, it is vulnerable against both attacks, both online attack and offline attack. Yeah, very good question. So that's why we need a second primitive called threshold oblivious pseudo-random function. It is a PRF function between a bunch of servers and a client. First, there is a pseudo-random function PRF key shared among the servers. And then the client can pick arbitrary input X to the PRF. And then they run this protocol, this TOPRF protocol. At the end of the protocol, the guarantee is that if there are T-valid responses from the servers, then they can be used to jointly recover the PRF output on this input X under the PRF key K shared among the servers. And the security guarantee is that if up to T-1 servers are corrupted, they cannot recover the PRF key K or compute the PRF function on any input X. And this is called oblivious PRF because the key K is hidden to the client and the input X is hidden to the servers. This is the primitive. Any questions on this? Yes?
Sorry again, so the same X gets sent to all of the servers, or in this case, is it different X?
The client is using the same X, but it is not sending X to any server because X is hidden to the servers. So it will compute something and send something to the servers and get something back, but it will recover the function fk on the same X. Okay. Now we know these two ingredients and we're ready to make some pasta. First, in the global setup phase, there is two keys shared among the servers, one key for NITTG and one key for TOPRF. And then when the user signs up, it will use its username and password as the input to the TOPRF and run this protocol. At the end of the protocol, if there are T-valid responses, then it will recover the PRF output Y, and then it sends back Y to every server. So every server will store the username along with the PRF value Y locally. That's the end of sign-up phase. And then when the user is requesting for a token, it will again use its username and password as the input to the TOPRF and run the protocol, recover Y, and send Y back to every server. Every server will verify the Y is correct. If it is correct, then it will use the secret key share for the NITTG scheme to generate a partial token. If there are T-valid partial tokens, it can be used to recover a real token. Okay, so in this case, it solves the previous issue that we had for offline attack because if up to T-1 servers are corrupted, they cannot jointly compute the PRF function F on any input X. So even if they have the value Y, they cannot do offline attack. Yes?
It's a little bit like you sort of replaced the password with Y, which is nice. It's more random, but it's still like a password. Like if somebody now steals the Ys, now they can.
Yeah, that's a very good question. We will talk about that later. Yes.
So if Y is already stored on the server, why not store it on the client? Why do you have to do this again?
Oh, because the user only remembers its username and password. It cannot remember anything else.
Security-wise, it will not degrade anything if you store Y on the client.
if it stores y locally, that's I think that is in our setting. We don't want the user to remember anything else. Normally, when it's just a natural setting. If you remember something else, then it will make things easier, but it will make life harder for the users.
Yeah.
We want them to just remember the username and password, but
sure.
nothing else.
I mean, but security-wise, because it's already stored on the server, so whatever it is vulnerable against, it will not.
Yes. If the user can store more things, then things will be much easier. Yeah, they can just share a secret between the two, and then every time you're using the same secret and so on. Any other questions? Yes.
So why does y depend on the secret keys of all the servers?
Yes.
And so then how is it? So does in the setup, does the user need to communicate with all the servers or just the threshold?
They don't have to talk to all the servers. It's but it's a little bit tricky because if you just talk to a threshold number of servers, then the other servers does not store y at all. They don't know y. So you have to talk to all the servers and let them know the value of y.
Okay, but you could set up y with only the threshold and then distribute y to all of them. So then what stops one server from creating their own simulated set of servers who all have secret keys, and then since y is independent of which servers sort of input to it, or is it independent in that way?
So you're saying, actually later in this talk, we will reduce the number of rounds in user sign up to just one round. Right now it has 3 rounds, but later there is just 1 round. And maybe later it will be clearer.
I think you're also assuming that there's authentication, right? So the client knows which server he's talking to.
The client knows which server he's talking to. It's not necessary, actually.
Oh, okay.
Yeah.
But the servers do some kind of setup where they get, like, do they have to do some protocol before you even start this where they get some nicely?
In the global setup, we assume the global setup is kind of a trusted setup. The secret keys honestly shared among the servers.
So you couldn't make up other servers because they wouldn't have the right secret keys.
Okay, but here there is still an issue as Melissa raised up. But before that, let me talk about how to reduce the round complexity. Because right now, the number of rounds in requesting for tokens has 4 rounds. 2 rounds to recover the PRF value y, and 2 rounds to send y back and gets the partial tokens. How do we reduce the 2 procedures to just 2 rounds, which is the minimum number of rounds? And minimizing the number of rounds is also for efficiency reason. Okay, so the idea is the following. The user is still using its username and password to run the TOPRF and recover the value y. But in addition, in the second round, every server will use the secret key for the NITTG to generate partial tokens and encrypt it under y. So if the user is using the correct password, then it will recover the correct y and then decrypt the ciphertext correctly. And if there are T-valid responses, he will be able to recover a real token. So in that way, we're reducing 4 rounds to 2 rounds. But there is still a subtle security issue because every server knows the same y. We'll see the issue in a second. Even if there is a single server corrupted here, what he can do is that he can pretend himself to be an honest client and then use any guessed password and run the TOPRF function. What he will get is something totally different from the correct y, but because he already knows the correct y, he can already decrypt these ciphertexts and recover a valid token. So this is what we call online attack, is that you have to talk to these servers in an online fashion, but ideally, if the server if the adversary is using an incorrect password, he shouldn't be able to recover a real token, a valid token. But in this case, he can. So this is not what we want. And we have to fix this. Okay. So the idea is that before we have the issue because every server is sharing the same Y. And here we will store different things on these servers. And here is how it works. When the user signs up, still runs the TOPRF and recover the PRF value Y. And after that, it's not sending Y back directly to the servers. Instead, it will derive a bunch of new keys using PRG or PRF, and then send these new keys to every server, a different key for every server. And then the server will store the username along with a different key. And then later, the server, when the user is requesting for a token, it will run the TOPRF and recover the same Y, derive the same keys, and so that it will be able to decrypt these ciphertexts encrypted under different keys and recover a real token if there are T-valid responses. Okay, so this solves our issue, but there is still a very, very subtle security issue here. I won't talk about that, but if you're interested, we can talk it offline. But this issue will be solved after I talk about, after the next fix. Okay. So next, what I'm going to talk about is how to reduce the number of rounds in the user sign-up phase. Because right now you have 3 rounds of interaction, 2 rounds to compute the TOPRF, and 1 round of sending the secret keys back. Okay. So if you think about it, in the global setup phase, there are 2 keys shared among the servers, 1 key for NITTG and 1 key for TOPRF. But these 2 keys are actually separate. They don't have any relation. So what we will do is that we will separate the 2 keys. The NITTG key will be shared among the servers in the global setup phase, but TOPRF key can be generated by every server, by every user locally. And here is the idea. So when the user is trying to sign up, it will generate a fresh TOPRF key. And because he knows the TOPRF key, it can compute the PRF value on its own and derive the secret keys K1 to Kn. And then in 1 round, it will send these TOPRF key shares along with these new keys to every server. And every server will store locally the user's password, a different key, and a TOPRF key share. The rest of the protocol is the same as before. The only difference is that the TOPRF key is not the same for every user, but it's different. But the NITTG key is the same. Because they're just separate. They don't have any relation between the TOPRF key or the NITTG key. So TOPRF key can just be generated by every user locally. Any questions?
So that's where it says TOPRF key. It's actually a different one for each.
Yeah. Different. It's actually TOPRF key shared. Yeah, and that solves all the issues, and we prove formally that it satisfies all the guarantees that we want. Okay, and last I want to talk about experimental results of our protocol. We implemented NITTG scheme for all these tokens, including symmetric key-based MAC, public key-based MAC, RSA-based digital signature, and pairing-based digital signature. And we also implemented TOPRF, and then we combine them to get our pasta. And here's the experimental results. Let me explain what the numbers mean in this table. So we only report performance for token request, but sign up is also fast because token request is used more often in practice. So we only show these performance. And then in this table, every row is a different type of token, symmetric key-based MAC, and so on. And every column is a different setting. I will explain what is a plain setting in a second, but the rest of the columns, every column is a different setting. For example, in this setting, it means there are 6 servers, and the threshold T is 3. Okay, so it is the number of servers and the threshold. And it is the performance in a LAN network with this much network latency, with this much network bandwidth and 0.1 milliseconds round-trip latency. And let me explain what is a plain setting. The plain setting is a setting that we discussed at the very beginning of this talk, where there is a single server holding the secret key, and when the user is requesting for a token, it sends its username and hash of its password to the server, and then the server generates the token. In this case, if the server is corrupted, then both the secret key and the password is leaked. So the question is, what's the extra cost of protecting both the secret key and the password? And here is the result. If you look at this table, we observe that the yellow columns are roughly the same. So the performance roughly only depends on the threshold. And that's natural because as a user, you only have to talk to threshold number of servers. You don't have to talk to all the servers when you request for a token. And if they are, the T servers are valid, then you can already recover a valid token. And similarly, when the threshold is 3, the numbers are roughly the same. Okay. And then when you compare our performance with the plain setting, there is a reasonable constant blow up in terms of efficiency, but the gap is slightly higher in the symmetric key-based MAC setting. The overhead is much bigger in that case. And the reason is that in the symmetric key-based MAC setting, the plain setting only uses symmetric key crypto, but our pasta inherently uses public key operations because of the TOPRF protocol. It needs public key operations. But we also show that public key operations are theoretically necessary to achieve our goal, to achieve pasta. And I won't go over the proof, but the high-level idea is that if you can achieve our goal, then you can do secure secret sharing, which is believed to be hard using symmetric key crypto only. So this gap is kind of inherent and unavoidable. Okay. And then we also tested on a WAN network with this much network bandwidth and 80 milliseconds round-trip latency. And here's the result. Similarly, it only depends on the threshold of the protocol. And then if you compare LAN network with WAN network, it is roughly plus 80 milliseconds round-trip latency. So that's why reducing the number of rounds is very crucial in this case. And we also, because our round complexity is optimal, so this is kind of the best we can achieve. And we have more, let me show some more experimental results. This is a time breakdown, namely how much time it spent on the client side and how much time it spends on the server side. And if you can see, as the threshold grows, the time it spent on the server side is roughly the same, but the time on the client side is growing. Okay. And we have more experimental results in the paper. If you're interested, you can take a look. But let me summarize at this point. We answered these 3 questions in this talk. First, what problem is Pasta trying to solve? We're trying to construct a new password-based threshold authentication protocol which protects both the secret key stored on the server and the user's passwords. And how does it work? We give a generic construction from two primitives, and then it is a general framework that works for various types of tokens. And is it practical? I would say, depending on our experimental results, I would say yes. And that's it. I hope you like this pasta. Thank you. Yes?
So you mentioned the game model at the beginning.
Yes.
And is there any incentive mechanism to make sure that the server do not behave maliciously?
We actually, in our game-based definition, we allow the servers to be maliciously behaving, but we assume there are at most T-1 servers corrupted. So if the server is corrupted, then they can behave arbitrarily, maliciously. They can arbitrarily deviate from the protocol. But we assume there are at most T-1 servers. Yeah. Yes.
In your evaluation, did you experiment with any versions of malicious servers? Like what would they have any? Would a malicious server returning some kind of wrong answer have any effect on the performance, assuming that there were T other servers returning correct answer, but maybe slower?
We did not explain. In our experimental results, we assume all the servers are honest. But yeah, if there are servers corrupted, then it will definitely affect the performance because maybe the token that are recovered from the protocol would be wrong, and then you have to try again and so on. It will definitely affect.
So the client could effectively get a little bit confused if a wrong answer is returned.
Yeah, that's true. Yes.
Yeah. What's the actual threshold oblivious sit-around function you use?
The same T.
Yeah, so what's the idea behind it? Is it Diffie-Hellman based or?
Oh yeah, it's Diffie-Hellman based.
Okay.
Oh, the assumption.
Yeah. No,
oh, it's not. It's not.
You're using?
Yeah, it's not a standard Diffie-Hellman assumption. It's some Q Diffie-Hellman assumption. Yeah.
So I'm a bit confused about the interaction between the non-interactive threshold token generation and the rest, because originally you introduced a non-interactive threshold token because all the parties could have the same. So if you have a generic, like traditional token, you have a party that hosts that could try to do a dictionary attack by guessing the password, hashing, and then generating a token and verifying is this token valid, as far as I understand. But now we say that the token is generated by the output of this oblivious, from the output of the oblivious PRF. Is that correct? From
the token itself is generated from the NITTG, not the TOPRF.
But the input to the NITTG would be the output of the PRF?
No, not really. Okay, let me see.
The message?
Let me see the protocol in 1 second. So here, the input to the tokens would still be the message. It will not be
the username and password.
Or something else. Like for example, the token, the message to the token could be my username and a timestamp. So that's normal. It is the same token generated as before, but the output Y is just to use to derive the keys and then decrypt the ciphertexts. It has nothing to do with the tokens.
Right, so the hash before was used for authentication, not for generating the tokens.
Yeah, the hash before also has nothing to do with the tokens. It's just verifying the user's credentials.
I see.
So that's why we can separate these two things. The NITG and TOPRF keys can actually be separate. They actually, yeah. As you can see here, this is just for these keys, and the tokens are generated separately. Does that answer your question?
But then so why do you still need the token generation to be thresholded? You couldn't. How do you use it to do a dictionary attack?
Oh yeah. So because we want both security definitions, one to protect password want to protect the secret key. If you're
Right.
using the same key to generate tokens,
Right.
then the other is not guaranteed. If one server is corrupted, then he can already use the secret key to generate valid tokens. Yeah, that's a good question.
Thank you.
Any other questions? Okay.
Thank you.
Yes. Oh.
Sorry, go ahead.
Have you tried different OPRS for your protocol, or have you just done experiments with the single one?
With a single one, we didn't try other, but it's a generic construction, so you can type in any TOPRF. Yeah.
Yeah. Payhan.